Okay, in this video we're going to talk about something called extrema. And extrema is just a fancy word that means extreme values of a function, or maximum values and minimum values. So when you don't want to say maximums and minimums, you just simply say extrema. So let's talk about extrema. There are two types. There are relative maximums and minimums, and then there are absolute maximums and minimums. So let's take, for example, this point right here. And I'm going to draw a circle, and in this circle I'm going to say that this circle represents Texas, because that's where I live. And so this point right here, if I'm just looking at Texas world, I would say that this is a minimum value. So I'll call that a relative minimum, meaning it is a minimum value relative to this circle alone, this Texas circle. But if I were to compare this point to, let's say, the entire graph, which we'll call the United States, then this point is not the absolute lowest point on the graph, because as you can see clearly that the yellow arrow goes well below this point, and so does this arrow here. And so this is a relative minimum, but it is not an absolute minimum. Now let's go over to here, and we're going to draw a little circle, and we're going to also call this Texas as well. So this is Texas, and inside Texas world, that is the highest point inside Texas world. So we will call that a relative maximum, because in Texas world, that is the highest point. But it is also the highest point in the United States. So if I were to draw a circle all the way around, I guess that's more like an oval. If I were to draw an oval all the way around this entire graph, this point right here would be the highest point on the entire graph. So we could also call this an absolute maximum value. So there are absolute extrema, and then there are relative extrema. Next, we're going to talk about increasing and decreasing intervals. And the key here, there are two keys. First of all, you want to read the graph like you're reading a book. You want to read it from left to right. The second thing that you want to do is you want to use x values only. Only x values. That's very important. Notice that I didn't put any y values on this graph alone, because what we're going to do is we're going to list the intervals where the function is increasing, decreasing, or constant. Let's start with increasing. All right, so this function is increasing. Well, if we trace the function, we can see that it's increasing here, and it is increasing from when x is negative infinity, not the y, okay? It's not that it's coming from a negative infinity in the y direction, it's coming from negative infinity in the x direction, meaning as x, starting from negative infinity, and it continues to increase, it increases until x gets to -1. Now, union, because it increases again between 4 and 6. Between these two x values, the function increases. So 4 and 6. And that's all. And it's constant between 1 and 3. So we'll say 1 and 3. And then it's decreasing. It's decreasing, well, it's increasing, constant. It's decreasing between x's 3 and 4. So 3 and 4. And we'll use parentheses for all this. And then in union with, it's increasing now, but it starts to decrease when x is 6. Now watch this. It continues to decrease as x moves towards positive infinity. Notice it's not negative infinity. That would be the y value. We don't want to use the y's. We want to say that it is decreasing when x starts at 6, and it continues to decrease as x moves towards infinity. Let's see how this works on a few problems. Okay, so example 1, use the graph of each function to estimate the intervals to the nearest 0.5 unit on which the function is increasing, decreasing, or constant. All right, so here we have the vertex, and we can see that the function is decreasing. So we will say that it is decreasing from negative infinity, meaning it's starting to decrease from way back here is when it's decreasing, and it will continue to decrease until x gets to 1, 2. So x is 2, so that is the only place that it's decreasing. And now it is increasing. It starts to increase right here, and that's when x is 2. And it will continue to increase as x moves towards positive infinity. All right, letter B, it's pretty simple here. It's going to be increasing here. So we'll do that first. So increasing from negative infinity, and it continues to increase until x gets to 1, 2, negative 3. And then there is no decreasing interval, so it's constant from negative 3, and it will continue to be constant as x moves towards positive infinity. Okay, so in example 2, it says to estimate and classify the extrema for the graph of each function. All right, so once again, this is what we started the video on. If I look at that point right there, and once again, if I look at just this little area right here, then I will call that a local maximum. So we will say, let's see, negative 1.5 and 2. So I'll say, okay, local max at approximately negative 1.5 and 2. And as another maximum right here, and that's going to be at over 1 and up 1, 2, 3. So we'll put, there's another one at 1, 3. All right, now, because this point is the highest point on the entire graph, I will also call that an absolute max. Absolute max at 1, 3. Now, there's a point right here, and that's going to be a minimum value. So we'll call that a local or relative. They mean the same thing. Local or relative minimum. And that's going to be at, looks like negative 0.5, negative 0.5. So negative 0.5 and negative 0.5. All right, and let's do the same for this one. Well, I see a relative maximum there, so I'll call this a local max. And that's going to be at negative 1, 2. There's another little max right there, and I'll call that, 0.75. 0.75, and looks like up 0.5. And looks like there's a minimum here and a minimum here, and they're both local or relative. And the reason is because this arrow means it goes up forever, and this arrow means it goes down forever. So there is no absolute max and there's no absolute minimum. But these are local. So there's a local or relative minimum at 0, 0. And then there's another one at, looks like 1, 2, 1, 2, 3, 4. So 2, negative 4 approximately. And that's all there is to this. Okay, for the sake of time on this video, we are going to skip the calculator problems C and D from example 2. They are literally exactly the same as the non-calculator problems. You just need to plug those functions into the calculator and use your calculator to find the maximum and minimum points, and use those to discuss the increasing and decreasing intervals. All right, we're going to move on to average rate of change. When you see the words average rate of change, I want you to immediately think of slope. That's exactly what this is. This is something you've done many times before in your algebra curriculum. y2 minus y1, maybe let's write it this way. y2 minus y1 over x2 minus x1. It's just slope. Now, in order to get slope, you need 2 ordered pairs. Now, I want to caution you on something. This is not an ordered pair. We know it's not because it doesn't have parentheses. Plus, it says that it is an interval. So this is an x value, and this is another x value right there. So that's x1 and this is x2. It's basically saying between these two x values, find the slope. So what we have to do is we got to get the matching y values. Take the 2, plug it in here. So f of 2 is going to be 2 to the third minus 2 times 2 squared minus 3 times 2 plus 2. 2 to the third is 8 minus 2 squared is 4 times 2 is also 8. And then we have negative 6 and plus 2. 8 minus 8 is 0. Negative 6 plus 2 is negative 4. So my first ordered pair is 2, negative 4. All right, so let's now plug in 3. This is going to be a little messy here, but we're going to work it out. 3 to the third power, and I'll put parentheses around that, no big deal. Minus 2 times 3 squared, minus 3 times 3 plus 2. 3 to the third is 27. 3 squared is 9 times 2 is 18. And minus 9 plus 2. 27 minus 18 is 9. 9 minus 9 is 0 plus 2. So we have 3 comma 2. So now we need to find the slope between these points. So that is going to give us 2, which is y2, minus a minus 4 divided by 3 minus 2. So if you're going to use this y minus that y, you must use this x minus that x. So 3 minus 2. 2 minus a minus 4 is a positive 6, and 3 minus 2 is 1. So our slope for part A is simply 6. Okay, for the sake of time, I am going to not show all of the calculations for part B here, but the same rules apply. So we're going to plug negative 5 in, and when you do that, you'll have, if you do all the calculations, you'll end up getting 455. And then when you plug in negative 3, you'll end up getting 15. So my ordered pairs are negative 5, comma 455, and negative 3, comma 15. So I'm going to do the slope over here. So 455 minus 15 over negative 5 minus a minus 3, double minus. And that's going to give you 440 over, well, if it's a double minus, it's really plus. So that's going to be negative 2. So that's going to end up giving you negative 220. Okay, so the final example on these notes is, let's say we have an object that is dropped from a high place, and this formula represents the distance that it has traveled. Well, we want to find and interpret the average speed of the object from 2 to 4 seconds. So average speed is going to be the total change in your distance. That delta means change. Change in your distance divided by the change in time, right? So if I were to go from here to Houston and I would go 200 miles, that's my total difference in my distance. And let's say it took me 4 hours. 4 hours. Then that means my average speed was 50 miles per hour. I didn't go that fast the whole time, but that was my average. That's what we're going to do here. So we're going to plug in 4 into this function. So d of 4 is going to be 16 times 4 squared. All right, and then d of 2 is going to be 16 times 2 squared. And so then what we end up having is 16 times 16, and 16 times 16 is 256. So the distance that it is at 4 seconds is 256. The distance or position that it was at 2 seconds is going to be, well, this looks like that's 4 times 16, so that's going to be 64. So it has changed its position by 192 feet. So 256 minus 64 over 4 seconds minus 2 seconds ends up giving us 192 feet divided by 2 seconds. So the average speed was 96 feet per second.